With indices out of the way on this indices and logarithms playlist, we now move on to logarithms. And in this video, we're looking at the meaning of logarithms. Okay, so meaning of logarithms, the inverse concept. Of course, we take indices and logarithms together because they are inverses of indices are inverses of logarithms. Logarithms are inverses of uh, indices, right? So by the end of this lesson, you will be able to correctly interpret logarithmic statements, instantly convert between exponential and logarithmic forms, understand and apply domain restrictions, and use common logs and natural logs effectively on a calculator. Okay, so let's go straight to the first part, the core idea. Logarithms are inverses of exponents, just like I mentioned earlier. They are inverses of exponents. A logarithm answers the question, to what power must the base be raised to obtain a given number, right? So, to what power must the base be raised for you to be able to get a particular number? That's the question logarithm answers. For instance, you have log to what power should a be raised so that you can get b. That's what this means. So log b base a equals x means that to what power must you raise a so you can get b? And the answer is that you raise a to power x so you can get b. All right. So what we call base for indices is still base here, except that now we write it in terms of log. So in the form of exponents, we have the base a raised to power the exponent x equal to the value. So, but here the log of the value to the base gives us the exponent. So in words, we say log b base a equals x. This means that a raised power x is equal to b. So you can easily translate from one to the other. So interpreting logarithms now, example one, if you have log 8 to base 2 equals 3, that means that, okay, I think I like to do it this way. You have log 8 to base 2 equals 3. So that simply means this 2, which is the base, carries 3 on its head. So 8 is equal to 2 raised to power 3. Or that simply means 2 raised to power 3 is equal to 8. And that's it. So to what power should you raise 2? So you can get 8. And the answer is 3 there. Okay. So the base carries the number on the other side on its head, in a manner of speaking. So log 8 base 2 equals 3 means that 2 raised to power 3 is equal to 8. Also, log 125 base 5 is equal to 3 means that 5 raised to power 3 is equal to 125. So that's how we interpret logarithms. And then we move on to talk about converting between forms. Okay, how do you convert from one form to another? So conversion pattern, log b base a equals x implies that a raised power x is equal to b. So example one, you want to convert to exponential form. So like what we've been doing, log 8 base 3 equals 4 implies that 3 raised power 4 equals 81. So in the reverse, convert to logarithmic form, you have 10 raised power minus 2 equals 0.01. That simply means that the log of the value to the base of the 10 is equal to minus 2. That's what that is about. So you have um you have 10 raised power minus 2. 10 raised power minus 2 equals 0.01, right? So you write log, of course, the base is always 10, log to base 10, and this is the result, 0.01, and that is always equal to the exponent, like this. Okay, so you need to raise 10 to power minus 2 to get 0.01, like this. So the base is always, just once you figure out the base, then I know the exponent is going to be on the other side, then that works. So in short, um if I say 7 raised to power 3, uh, yeah, 7 raised to power 3 equals 343. So in log form, I just say that is log. The base is 7 because 7 carries 3 on its head. So the log to base 7 of 343 is equal to 3, like that. Okay. So with that done, we then move on to other things. Let's look at a quick drill practice where we convert instantly. So convert to logarithm form. 2 raised power 5 is 32. That's simply 2 carries, I mean, 2 raised power 5 equals 32, right? That will be log 2, log 32 to base 2 equals 5. That's it here. Log 32 base 2 equals 5. 7 raised power 2 equals 49. Just identify the base. That makes everything easy. The base here is 7. So log 49 base 7 equals the power 2. Then, uh, so you know the power is the answer at the end of the day, is at the right hand side. So the base is 4, the power is 0, the value is 1. Yeah. So we just say log. So generally speaking, we say log of the value. So you have base raised to power, or call it index, okay, is equal to value. Okay, so this is in exponential form. So in logarithm form now, to simply be log of the value to the base equals power. Okay, if you understand it like that, then it makes everything pretty easy. So base raised to power equals value. Then if in log form, that means log of value to the base is equal to power. Okay, so here 4 is base, 0 is power, 1 is value. So log of value, which is 1, to base 4, which is base, equals 0, which is power. Then you have 9 raised per half equals 3. So log to base 3, I mean log 3 rather, base 9 is equal to 1 over 2. So that's quick um consideration of all we've been learning so far. Now, there are domain restrictions, just like in the case of exponents. If you remember, for exponents, we talked about some conditions for something to be an exponent. Imagine that you have a raised power x, okay? So for a raised power x to pass as an exponent, first of all, a must be greater than 0. It has to be positive. In addition, a should not be equal to 1, because if a is negative, then um, this, it will not serve the purpose. And if a is equal to 1, 1 raised power x, whatever x is always 1. So it doesn't help anything. So we need these two conditions, that a is greater than 0 and a is not equal to 1. So that also transfers to the idea of exponents. So for log b raised to log b base a to be defined in real values, first of all, same two conditions like before. A must be positive, then a must be not equal to 1, and then in addition, the value has got to be greater than 0. Now, it is understandable to know that the value is greater than 0, because no matter what exponent you take, you end up getting um you end up getting a positive value, for any kind of exponent. Even if the power is negative, you end up getting something positive. So b, has the value is always greater than 0, just like a itself is greater than 0, and it's actually not 1. So why do we have this? The base must be positive, all right, and the base cannot be equal to 1. And finally, the argument must be positive. The argument is what I call value in the other case. So invalid examples of log now. So log 8 base minus 2, this cannot work because the base has got to be positive, okay, and minus 2 is not. Then log 5 base 1 is not possible because the base has got to be not equal to 1. Then log minus 7 to base 3 is not possible because the argument minus 7, or the value, like I said, should be positive too. So these three conditions are restrictions on any kind of logarithm you come across. The base is positive, the base is not 1, and then b is greater than 0. So if you want to combine these two together, so you can say a is greater than 1, right? So if you combine these two conditions, we say a is greater than 1. So a can then be 2 upwards. Okay, so like that. Now we move on to the next. Now we have two main types of logarithm. I think I talked about that in a previous video. We have common logarithms, and common logarithms is simply logarithms to base 10. All right. Logarithms can be to any base at all, but we have some special logarithms like logarithms to base 10. If no base is written, for instance, base 10 is assumed. So if you see log x, just know that is log x to base 10, and that is what is called the common logarithm. So example of base 10 will be something like if you have log 100 is like log 100 to base 10, which is 2, because you need to raise 10 to power 2 to get 100. So here, that means you have 10 raised power 2 equals 100. If you also have log 0.001 equals minus 3, that means 10 raised power minus 3 is equal to 0.001. So if the base is omitted, just know that that is 10. Okay. Then apart from the common logarithm, we also have the natural logarithm. Okay. That comes naturally if you like. So um you have natural logarithms, that's to base e now. So common logarithm base 10, natural logarithm is base e. Now, and it is written as ln x. So when you say ln x, it means you're talking about log of x to base e, where e is this special value 2.718. Okay, and this I think we see this number in the Euler identity, which is what's that one? E raised power I theta equals 1 or something like that. E raised power I theta plus 1 equals 1. So E is one of those special values in that expression. So, and from here now we see that ln e raised power 4 is equal to 4, because we are going to see that ln is the inverse of it, so they cancel themselves out, and you end up getting 4. So ln 1, of course, is 0. Ln of 1 to any base at all, ln of 1 to log of 1, in fact, to any base will always give 0, because any for whatever base you have, okay, I guess I want to write there. Okay, because of course e raised power 0 is 1. I think this is the condition here. So as far as the argument is 1 in any case, so imagine you have log 1 to whatever base at all. So log 1 is always 0, because if this is a, or anything you want to call it, it can be a, it can be 10, it can be anything at all. It will always be that a raised by 0 equals 1. So if you like, ln 1 equals 0 still, because e raised by 0 is also 1. Okay, if you like, say log 1 is equal to 0. I mean, log 1 is always 0, in fact. So here, since the base is not written, that means 10 raised by 0 is equal to 1. So the log of 1 to any base at all is always 0, because any number raised by 0 is equal to 1. Okay? Now, some calculator skills you may want to master. Imagine that you have, uh, most calculators have log, which is base 10, and ln, which is base e. So you want to find log 7. Well, I don't have a calculator here like that, but I like to use, okay, maybe I can, should I, okay, I like Desmos, right? Desmos helps with most things I need to do for graphing. Okay, we have a scientific calculator here. Excellent. Okay, yeah, we have this. So to use this now, if I need to compute log 7, so I just come to, do we have log somewhere? Okay, I guess we have to look for it. Functions, is there log somewhere? Yeah, this is log here, that I write 7. So, and this shows the answer to be 0.845. Okay, so we have 0.8451 to 4 decimal. This is 0.8451. Then, so we have that. On the other hand, it means that 10 raised by 0.8451 is approximately 7, because you're dealing with base 10. So let's try that. I'll open Desmos again. Right now I want to, okay, we are switching, right? So now I want to graph. So we already saw that log 7 is 0.8451. So it means if we say 7 raised to power 0.8451. So 7 raised by 0.8451. That's given approximately, that's 5, which is pretty close to, far from 7. So it means more decimal places will be useful. So 5098040014. Even at that, it's still very far from 7. So, but it's, oh, what did I do? Okay, this should be 10 raised power. Sorry. I was wondering why it's so far away. So, sorry, log to base 7. Sorry, it should be 10 raised power that. So, 0. 8451. So that's approximately 7, as you can see. Yeah, it should be 10 raised per that, not 7 raised per that. Okay, so that's how to punch your calculator. So, for example, 2, now we need to find lane 5. Okay, lane 5, we come to the scientific calculator. So, first of all, we can clear this out. So, lane 5, I come to lane, I have 5 here. That's 1.6094. 1.6094, and that's all we have here. 1.609. So that means because lane 5 is actually log 5 to base e. So that means e raised power 1.609 should be equal to 5, right? 1.609 raised power 5. Or I can still do that lane 5 here too. Lane 5, we get this. So it means that e raised to power 1.609. Okay, that's approximately 5. So the more I get the decimals, so if I take it to this, it's getting closer. 6094379 1243 1243. Okay, it's getting closer and closer like that. So almost 5 there. Okay, so solving simple log equations. So if you want to solve simple log equations, what do? You have for instance, example 1, log 5, log x to base 2 equals 5. So that simply means you have 2 raised power 5 equals x, and that means x is 32 easily. So x is 32. Example 2, ln x equals 3. That means e raised power 3 is equal to x. So if e raised power 3 is equal to x, then you just go and compute that. So e raised power, okay, e raised power, x is e raised power 3. So just come here and do e raised power 3. E raised to power 3. And that is 20.0855. 20.0855. That's 20.09 roughly. Then lastly, if you have log x equals minus 1. So that means the base, if the base is not written, you have 10. So log 10, that means 10 raised per minus 1 is x. And 10 raised per minus 1 is 1 over 10, which is 0.1, simply. All right. So how do you interpret graphs? Log graphs. So imagine you have exponential function y equals 2 raised power x. The logarithmic function is y equals log x to base 2. As you already know, if you want to try, so 2 raised power y equals x, right? So imagine y is 2x. So we can come to the plot. Y is 2 raised power x. So we just have 2 raised power x. See what the curve looks like. On the other hand, of course, we know they are inverses of themselves. So we now have log x to base 2. Okay? Log x base 2. Okay, so you can see they are opposing themselves like this. So that's what that looks like. So red is the exponent while uh, blue is the log. Okay, so we have that. So we see that for the key point is that the exponent passes through 0, comma 1. Okay, the exponent will always pass through 0, comma 1 because anything raised by 0 is equal to 1. So you see the exponent will always pass through 0, comma 1, this point here, 0, 1. On the other hand, the logarithm passes through 1, 0. So that's a very good example that one is an inverse of the other. So you see this one passing through 1, 0, as you can see here. So this one passes through 0, comma 1, and this one passes through 1, comma 0, like this. And then there are reflections across. So it means the two graphs are reflected across y equals x. So they are reflected across, or maybe you can say they are symmetric about y equals x. Imagine if we say y is equal to x now. So you just have that straight line. Or should I, if I do only x, I think that should work too. X, yeah. So you see they are reflected about y equals x. So then okay, yeah, we come to practice problems now. As usual, we have 20 of them. Let me see how many I'll be able to answer before this comes to an end. So I talk about practice problems. Okay, yeah. So let's go. We have first then like this. Okay, maybe I should just not bother about first then. Maybe I should do sevens if possible. Now convert to logarithm form. Of course, 3 raised by 5 equals 243. That means log 243 base 3 is equal to 5. Then convert to exponential form. That this log 64 to base 4 equals 3. That means 4 raised by 3 equals 64. Convert to logarithmic form. This means log 1 over 25 to base 5 is equal to minus 2. Convert to exponential form. 2 raised by 5 is 32. Evaluate. So evaluate this now. Aha. Well, we've not done the laws of logarithm, right? So if I want to evaluate this now, this is what I can do. Since we have not done the laws, if we had done the laws, there's a way we can do it. But to evaluate, I'll just say log 49 to base 7. Okay. To evaluate, to evaluate log 49 to base 7. Okay. What do? We can just say let log 49 to base 7 be equal to x. So using the law of indices now, 7 carries x on its head. So we have 7 raised power x equals 49. And we know that 7 raised power x, and we've learned how to solve indicial equations or exponential equations like this. 7 raised power x equals 7 raised power 2. So finally, we just say x is equal to 2. That's all. So, but by the time we do the laws of indices, I mean the laws of logarithm rather, in the next video, you see that I don't have to go through that step. So all I'll just need to do is 49 is 7 raised power 2. And if you have log of a number to its the same base, that will just give us 1. Just like when you have ln e, which is log e to base e. Okay. So you want to try all this out. Let me get one more. Okay. To rewrite this one in logarithmic form, it's just log of cube root of 3 to base 2 is equal to 1 over 3. Then yeah, evaluate ln 1 is 0. Any log of 1 to any base is 0. Okay. Yeah, I think that's pretty cool to deal with. So with this, I come to the end of this interesting video about the meaning of logarithms. Okay, let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Uh, don't forget to try your hands on the problems so you can actually be sure of how well you understand everything. So we have questions 1 to 7 here right now, 1 to 7. Then I move on to 8 to say 14. Okay, 8 to 16. 8 to 15, and then we see the rest. So try your hands on them. If you have subscribed already, I thank you very much for doing that. If you haven't subscribed, go ahead and subscribe. So that you don't want to miss, because you don't want to miss out on anything going on here. Subscribe, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you some special privileges like getting to see some videos first, or some videos being made for only you, or hanging out with me to discuss anything that interests you on this channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.